So now class, look at this one here. The graph for log x to the base of a, where a is greater than 1. For example, log x to the base of 2, log x to the base of 5, where base 2, 5, which is greater than 1. Okay, and we have the vertical asymptote at y-axis, for example, here. Okay, so the graph is sliding down, moving, approaching, getting close to the line of y-axis, but it won't touch or cut the line of y-axis. So it means that at this moment, this is the vertical asymptote of the graph. Okay, and the domain, okay, look at domain, the graph here, the domain approaching to 0 from right and to positive infinity. Okay, 0 to positive infinity, and the range or value of y is all values y being mapped through to the graph. So then it's all real numbers. And look at this one here now. The graph will oppositely from here. So when a lies in between 0 and 1, for example, log x to the base of 1 over 3, log x to the base of 1 over 2, okay? So then look at this one here now, and the domain and the range of the function. Okay, sketch the graph of log x to the base of half and log x to the base of 2, state the domain and range. What's the question just now? Fx equal to log x to the base of half and fx equal to log x to the base of 2. So class, for this one here, okay, so class, for function of log, I'm gonna use we call a general function. We call general definition of log. Okay, log 1 equal to 0, log 0, then the whole function is undefined. Okay, so I'm gonna use this. For example, for fx equal to log x to the base of half. Okay, so when x, this function inside, which is x, when x equal to 1, okay, log 1, then the whole function of y, fx, log 1 to the base of half equal to 0. Okay, why? Because, okay, log x to the base of half equal to 0, because the base of half to the power of 0, any numbers to the power of 0 will surely give you 1. So that's why log 1 equal to 0. Okay, and then when x equal to 0, because the function inside this bracket here, x equal to 0. When x equal to 0, where is the line of x equal to 0? Yes, x equal to 0 is along the y-axis here. Okay, along the y-axis is where the value of x equal to 0. Okay, so now the intersection point, x equal to 1, y equal to 0 here. We like to see what is the attitude of the graph when it's approached to the 0. Okay, between 1 and 0 here, just imagine if I have the value of x equal to 1 over 2. Okay, so f1 over 2 equal to log 1 over 2 to the base of 1 over 2. And this is 1 over 2 is 2 to the power of negative 1. Oh, wait. For this case, sorry. Okay, log half to the base of half is just like log a to the base of a, which is equal to 1. So log half to the base of half, yes, is positive value here. And then you may press the calculator when x, let's say 2, 3, 4, 5, okay, x equal to 2. Log, okay, x equal to 3. Log 3 to the base of half. For this one, let's try. Let me try. Okay. Log, okay, log 1 over 2 log 3 to the base of half equal to this one here, negative 1.5849 something. So when x equal to 3, log 3 to the base of half, the value is negative. In this case, the graph will be something like this. Okay, the graph will be something like this. Okay, is cut a line of x equal to 1 and sliding down that here, and this one moving up, getting close, approaching to the line of y equal to an x. There you go. So this is the function of fx equal to natural log of x to the base of half. Okay, now let's discuss the second function here. Okay, the second function, okay, the first function here, log x to the base of half, and second function here, log x to the base of 2. So then, log x to the base of 2, so when x equal to 1, f1 equal to log 1 to the base of 2 equal to 0. So when x equal to 1, y equal to 0, intersect here again. And then when x equal to 0, the whole function is undefined. So then y-axis now again become the vertical asymptote of this graph. Okay, now let's imagine if I put half here, 1 over 2, log 1 over 2 to the base of 2. 1 over 2 itself is a log 1 over 2 is 1 over 2 power of 1 or 2 power of negative 1. 2 power of negative 1 to the base of 2, negative, bring up here, negative 1 here, and log 2 to the base of 2, negative 1, log 2 to the base of 2, where this is equal to 1. 1 multiplied with negative 1, negative 1. So when x equal to half, the function is negative value somewhere around here. Okay, and then when x equal to 3, log 3 to the base of 2. Okay, log 3 to the base of 2. It is 1.548849 something, is a positive. So then the graph will be something like this. Okay, so this is the function of fx equal to log x to the base of 2. Okay, now what is the domain and range of both of this function? The domain and range for both of this function. Look at this one here, the graph sliding up, approaching to the line of x equal to 0, meaning that the value of x approaching to 0, and for this one too, approaching to 0, so then the domain is from 0 to positive infinity, and the range, look at this one here, okay, for all values of y, and also here, recall, involving all the values of y. So then the range is from negative infinity to positive infinity. Okay, sketch the graph of all this. Okay, so with these notes, class, Okay, vertical asymptote. Vertical asymptote means that vertical asymptote when x equal to 0 along the y-axis. Okay, so when fx equal to 0, when x equal to 1, when x equal to 1, natural log of 1 is equal to 0 or the y intersect here. Okay, the graph will be something like this. Okay, so for this one here now, when x equal to 0, vertical asymptote again, and also x equal to 0, vertical asymptote, means that the vertical asymptote for all these three examples is where it will along the y-axis. Okay, but then look at this one here now. Just imagine this 1 over 2x, we make it equal to 1 because we agree that log 1 equal to 0. So we must make sure that the function inside must be equal to 1. So 1 over 2x, make it equal to 1. Then x equal to 2. So intersect at y equal to 2. And this one intersect at y equal to 1. And what about this one here now? So again, we compare this 2x with 1 because log 1 equal to 0. So 2x equal to 1, then x equal to 1 over 2. So then it is 1 over 2 here in the graph intersect them. So three different cutting point at x-axis, which is the first is 1, 2, and half. Okay, so if we go sketch this on the same axis. Okay, for example, okay, there you go, sorry. Okay, and then x, which is half, 1, and 2 here. Okay, we get the first graph of this. Okay, and second graph. And the third graph. Okay, so intersect at 2. Intersect at 2 is for ln half x. This is natural log of 1 over 2x. And this one, the purple, intersect at 1, which is natural log of x. And the last final one here, this is natural log of 2x. So what is the domain and range for all these three graphs? Look at this all here, that we call the graph sliding down. We call approaching to the value of x equal to 0 here. So the domain for all these three graphs, I put it all together here, is from 0 to positive infinity. And the range, all the values, we call point up to the value of y here. Okay, from y, the value of y, from positive to negative infinity. So all the range is all real numbers. Okay, there you go. Sketch the graph of the following and domain and state range. Okay, ln x plus 1, a natural log of x plus 1, ln x minus 1, and 1 minus x. Okay, fx equal to ln x plus 1. Okay, Again, our reference here, natural log of 1 equal to 0 and natural log of 0 and the whole function undefined. Okay, so when x equal to 0, okay, fx equal to natural log of 0 plus 1 equal to natural log of 1. Then natural of 1 equal to 0. So when x equal to 0, fx or y equal to 0 intersect at origin point here. Okay, class. Okay, I forgot something. Let's make this function x plus 1. Let's make this x plus 1 equal to 0. Then x equal to negative 1. Okay, now I get it. Okay, wait. I think that I'm going to clear this first. Okay, just imagine that if we compare this x plus 1, make it equal to... Okay, let's make this one, compare this with x plus 1 with 1 here. And then x equal to 1, bring out here become negative, so 1 minus 1 equal to 0. And try again, f1. Now x equal to 0, f0 equal to natural log of 0 plus 1 equal to natural log of 1, and it is equal to 0. When x equal to 0, y equal to 0 intersect here. And then let's compare with x plus 1 equal to 0, where x equal to negative 1. Here, negative 1, meaning at this point, negative 1, x equal to negative 1 is a vertical asymptote of the graph. Okay, so just imagine that if I choose any value of x lies in between here, 0 and negative 1, which is let x equal to negative 1 over 2. So f negative 1 over 2, which is natural log of negative 1 over 2 plus 1. Negative ln half plus 1 is natural log of 1 over 2. Negative half plus 1 is equal to positive half. And natural log of half. Natural log of half, okay, for example, natural log of half, 1 over 2. It gives us negative value, negative 0.693, so on. The most important here is negative here now. Okay, so it means that when x equal to negative half, this is the coordinate. So the graph will be something like this. There you go. So this is fx equal to natural log of x plus 1. Okay. Next question, fx equal to natural log of x minus 1. Okay, again, this is our reference here, log 1 equal to 0, and log 0 and the whole function is undefined. So let's compare this, x minus 1 equal to 1. Then x equal to 2. Yes. Okay, let's try. Natural log of 2 minus 1 equal to natural log of 1, and natural log of 1 equal to 0. So when x equal to 2, y equal to 0. 2, 0 here. Okay. And compare again, let's compare this x minus 1 with 0. X minus 1 equal to 0, then x equal to 1, somewhere around here. Okay, so when x equal to 1, 1 minus 1 equal to 0, natural log of 0 is undefined. So x equal to 1 now become the vertical asymptote. Okay, now we like to find a graph we call the attitude of the graph, the behavioral graph, whether it's from down here cutting at 2 and moving up, or from up here cutting down and slowing down here. But most of the time, as we know that Class, earlier when you mentioned about log x to the base of half, the graph will be something like this, right? And then log x to the base of 2, and the graph will be something like this. So which I think that we can predict what is the graph or how the graph looks like for this one here. Okay, there you go. Would you like to try? Okay, let's find it one here. Let's make the recall. Just assume that value of x, take the one here, 1.5. Okay, natural log of 1.5 minus 1 is natural log of 1.5 minus 1 is 0.5 or 1 over 2. And natural log of half, again, it is a negative 0 point something. So the value of half when x equal to 1.5, the value of the whole function is negative down here. So this is the function of fx equal to natural log of x minus 1. So what is the domain of this function? X approaching to 1 and to positive infinity, so 1 to positive infinity. And the range of this function? The range is all real numbers from positive to negative, so all real numbers. Okay, now, again, okay, so again, natural log of 1 equal to 0 and natural log of 0 and the whole function undefined as our reference here now. Let's compare this. 1 minus x equal to 1. Negative x equal to 1, bring it here become negative, so 1 minus 1 equal to 0, then x equal to 0. Okay, when x equal to 0, 1 minus 0 equal to 1, natural log 1 equal to 0, it cuts at the origin point of 0, 0 here. Okay, natural log of 1 minus 0 equal to natural log of 1, and natural log of 1 is equal to 0, x equal to 0, y equal to 0 here. And then let's compare this with this one here. 1 minus x equal to 0, then negative x equal to negative 1, and x equal to 1. Okay, x equal to 1 here. Okay, so now, once we compare 1 minus x equal to 0, what does it mean? Yes, the whole function undefined, so x equal to 1 now is now recall the vertical asymptote of the line. Okay, so then now, let's see how the graph looks like when we choose any value of x. Let's say x between 0 and 1 here is 1.5, 0.5. So natural log of 1 minus 0.5 is natural log of 0.5. And natural log of 0.5, again, you may test using your calculator, it gives us a negative value. So it's down here. So the graph will be something like this. Okay, this is we call the difficult part of sketching this kind of graph. I need to adjust my hand. Okay, cut it here and slope down that here. Okay, there you go. So now, what is the domain and range of this function? The domain is all values of x from negative and approaching to 1 here. So the domain is from negative infinity until 1, and the range is all real numbers, right? The value of y, so it is all real numbers. Okay, now given fx and gx, compute f, gx, and gfx and state relation between f and g. So now, what is the function of fx? Fx equal to natural log of 3x plus 4, and gx equal to e to the power of x minus 4 divided by 3. So let's find out the first one, that f gx, where gx equal to e to the power of x minus 4 divided by 3. And class, composite function is a function is a process where we substitute this function of g into an x of the function f So natural log of 3x, where x equal to now ex minus 4 divided by 3 minus 4. Okay, plus 4 here. Okay, so 3 divided by 3, then you get 3 e power of x minus 4 plus 4. So 4 minus 4 equal to 0. Then natural log of ex, bring the x in front here. So x natural log of e, where natural log of e equal to 1. 1 multiplied with x equal to an x. Okay, now let's try with g fx. Okay, again, the function of fx, natural log of 3x plus 4, and substitute the whole function into an x of the function g. E natural log of 3x plus 4 minus 4 divided by 3. Okay, look at this one here. Okay, sorry. Minus 4. Okay, look at this. E and natural log is cancelling each other then. Okay, so with this process, you find out yourself, you can find out this process in the lecture, we call in reference book or lecture notes. Okay, so this one will straightly come out with 3x plus 4 minus 4 divided by 3. So then 4 minus 4 equal to 0. 3 divided by 3 equal to 1. So what's left here now? It's an x. So what is our conclusion then? Our conclusion is simple, where gx is an inverse of the function fx. Okay, there you go. Okay, so now, given e power of negative x plus 2, find f inverse, take the domain and range, and sketch on the same diagram e power of negative x plus 2. Okay, find f inverse, take the domain and range, and sketch. Okay, I'm comfortable using this method. Let the function fx equal to y, e to the power of negative x plus 2. You may also use what we call any other method that related, that been taught in the lecture, or might be something we call your prior knowledge that been taught last time during your SPM. Okay, so I'm doing this. Let's first come up with this equation of y equal to fx, y equal to the whole function with the variable of x here, and we're going to form the function into the change into the form of f equal to fy. Okay, so bring this 2 to the left side, positive become negative, so e power of negative x equal to y minus 2. So to eliminate this e, the constant of e, we're going to come out with natural log ex equal to natural log of y minus 2. And bring this to the front here. Okay, and ln e, natural log of e, negative natural log of e equal to natural log of y minus 2, and this should really give you 1. So negative x equal to natural log of y minus 2, then x equal to negative natural log of y minus 2. So class, the f inverse of this function here now is negative natural log of x minus 2. Okay, now okay, so class, look, let's take a look at this. Okay, okay, when x itself, when x equal to 0, e power of negative 0 equal to 0, e power of negative 0 equal to e power of 0 equal to 1. 1 plus 2 equal to 3. Okay. When x equal to 0. When x equal to 0, then f0 equal to 3. So when x approaching to positive infinity, when x is getting bigger, e power of negative x is getting smaller, approaching to 0. Please do remember what I told because I explained just now, okay, earlier of this video. When x equal to positive, but since that this is e power of negative x, so when x is getting bigger, e power of negative x is getting smaller, approaching to 0. Approaching to 0, we assume that everything equal to 0. Plus 2 equal to? Yes, approaching to the value of y equal to 2. Okay. When x is getting bigger and bigger, the graph approaching to the line of y equal to 2 here. Then fx approaching to 2. And when x is getting smaller, negative infinity, what we have here right now, e power of negative. X is negative 2. So negative multiplied by negative become positive. So when x is getting smaller, then f is getting bigger, approaching to positive infinity. So the guys, girls, this is a graph looks like. This is how the graph looks like here now. Okay, so this is fx. Okay, class, to sketch the graph of f and its inverse on the same axis, we need a line of what we call a reflective mirror here. A line of y equal to an x. Okay. So now, just imagine that if I, transfers this line of y equal to 2, now become x equal to 2. Okay, and then the intersect at y equal to 3, we switch here x equal to 3, and this is x equal to 2. Okay, because we like to sketch the graph of f and its inverse on the same axis. So this is our reference now. The graph cut at y equal to 3, and just imagine that if we bring this to this side, the graph cut at we call the point of x equal to 3 here. And then the graph sliding down, approaching to the line of y equal to 2. So just imagine that here the graph sliding, approaching to the line of x equal to 2. So now, okay, something like here. So this part we call shift, or we're going to call reflect to this part here now. Okay. And then this part we call reflects from here. Okay, sorry. There you go. Okay, this is the inverse of the function f. This one here. Okay. Okay, class, which I think that's all for today. We call the part 1 of the lecture of topic 404. Okay, 5.4, that involved with exponential and trigonometric function. The last final part for trigonometric function, we will do it later. So that's all for today. Thank you very much, and I do hope that these videos benefit you all. And that's all. Thank you. Assalamualaikum warahmatullahi wabarakatuh, and have a nice day.